Hey there, welcome to lesson 215. We're going to be covering this in the next 2 days. I structured this lesson just a little bit differently. So I'm going to explain in this video kind of how to do these problems. But then tomorrow during our live session, you're still going to have to tune in live, but it's not going to be just me like talking to you. What I want you to do tomorrow is in real time during your live session, log into Canvas, and you guys are actually going to be doing 66 and 67, okay? The reason that I decided to do it that way, and I think it'll work the way I want it to, I'm hoping, the reason I wanted to do it that way is because if we were in class, like those would be ones that I would say, okay, now do those on your own and let's see how you do. All right, so today I'm gonna go through the first part of this. Tomorrow during Canvas, do those 2 problems. I want to see how you do. Okay, so we're still kind of doing it the way we would have done it in class, but just the virtual version of that, I guess. So in Canvas, you still have to log in during our live session. They will only be available during your live session. Okay, so for third hour, that means it starts at 10 and you will not be able to see it after 11. Okay, so log in during our live session and make sure you get that done. All right, for 7th hour, it's going to be available at 1:30 and will only be available until 2:30. So make sure you log in and get that done during our live session. All right, so like you don't have to sign up for our Google Meet tomorrow because that is going to be your live session. And again, I think it's going to work the way I want to. It'll give me kind of a little progress check to see how you're doing with all of this stuff. That's kind of the purpose of it. All right, having said that, let's jump into 215. So we are going to model some data. So you're going to be looking at some situations and you're going to be writing some equations about those situations. Now, so far, we have done a lot of work with the vertex and we've done a lot of work with horizontal and vertical shifts. We've talked about the A value and the fact that it has to do with the orientation, but also the stretch and compression of your parabola. We haven't really talked about like how to find the A value yet though, like if it's not given to us. It's always been given to us up till this point. So that's going to be one of the focuses of this lesson is how do we find the A when we don't know what it is, okay? So let's set up this first problem. In the past few lessons, you've determined how to move graphs of parabolas around, that is to transform them on a set of axes. You've also learned how to write quadratic equations and graphing in standard form. In this lesson, you will put these new skills to work as you use parabolas and their equations to model situations. Okay, so here is a situation that we are going to model today. All right, this is called jumping jackrabbits. It says the diagram at the right shows a jackrabbit jumping over a 3-foot fence. To just clear the fence, the rabbit must start its jump at a point 4 feet from the fence. Sketch a situation and write an equation that models the path of the jackrabbit. Show or explain how you know your sketch and equation fit the situation. Okay, so let's just talk about this picture for a sec. So we can see that the fence is 3 feet high. Oops. Okay, but then it says that he has to start from 4 feet in front of the fence to clear that fence. So if this is truly a parabola, theoretically, if he starts 4 feet before, he's going to land 4 feet after. All right, so that's where the 8 feet comes from. And then the fence we're setting it up so the fence is right in the middle. Okay, so now let's see these discussion points. We're going to be answering these questions as we go. How can we make a graph to fit this situation? What information do we need in order to find an equation? And how can we be sure that our equation fits the situation? Okay, let's keep those in mind. Here is where the work is going to happen. So for 65, we want to sketch a path of the jackrabbit on your paper. Choose where to place the X and Y axes in your diagram so they make sense and make the problem easier. Label as many points as you can on your sketch. We're going to explore this using the E tool in a second as well. So for part A, it says, what is the shape of the path of the jackrabbit? What kind of equation would best model the situation? Well, I kind of already told you, right? It's going to be a parabola, right? A parabolic path, which means that the equation is going to have to be quadratic, right? So that means we're going to have an x squared in there somewhere. Okay, so we know that already going in just based on the original picture. Part B, at what point on your graph can you tell, at what point on your graph can tell you about the values of h and k in the equation, and then write the values for h and k into the general equation. Is your equation finished? Okay, so h and k, remember, they refer to the vertex. Okay, Now, before we sketch this, I just want to show you the E-tool. You can do this on your own as well if you'd like. Where are the rabbits? Come on, there they are. Okay, so in order to move the rabbits, you have to use these little sliders. So I'm gonna have the rabbits sit right on the x-axis, and then move over, there we go. So now that's a distance of 8, theoretically, right? So it looks like if we start at 0, we end at 8, vertex is right in the middle, and then up 3. Okay, so we're starting at the origin. We're gonna move over 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, the vertex is right in the middle. 1, 2, 3, 4, and it's a 3-foot high fence. 1, 2, 3. Okay, so this is our parabola. Okay, so the first question was about the h and the k. Well, that would be our vertex, right? So our vertex is at 4, 3. So if we were to put that into our general equation, y equals sum a, we're not sure, we know it must be negative, right, because it's upside down, x minus 4 squared plus 3. That's what we have so far. All right, then it said, is your equation complete? Well, no, because we don't know what the a value is. All we know is that it's going to have to be negative because this is an upside down parabola, right? Okay, that's the best we know. We don't, it looks like it's stretched out from the original, so there's got to be some number in there as well, too. Okay, part C, it says, with your team, with me, find a strategy to find the exact value of A. Will any of the points on your diagram help? I will share this strategy with you. Okay, here's where the work comes in to find A. We know the vertex, right? We also know 2 points on our graph, 0, 0, and 8, 0. Those are our x-intercepts, right? Look at your equation. You have an x and a y in your equation, right? We know from any equation, no matter what it is, you can plug in values for x and get a y, and plug in a value for x and get a y, right? Why would this be any different? Okay, let's pick this point, just because zeros are easy. Really the only reason. If you want to use 8, 0, great. So if we use 0, 0, that's a point on our parabola, right? So I'm going to plug that in. This is an x, this is a y. 0 equals a times, here's my x, minus 4. Right? I just plugged them in. Again, if you want to use 8, 0, go for it. Simplify. Right? Simplify again. Now solve. Subtract the 3 over. Okay, divide. There's your 8. Right? It's negative, so it opens upside down, right? It's less than 1, so yeah, it's going to be wider. Okay, so final answer, y equals -3/16 times x minus 4 squared plus 3. Okay, that is our equation. Part D, what are the domain and range of your model? Domain from 0 to 8, right? 0 less than or equal to x, less than or equal to 8. The range 0 to 3. Y 3. There's our domain and range, folks. Okay. E. Did any team in your class get a different equation? If so, write their equation and show how it can also model the path of the jackrabbit. What choices did that team make differently that resulted in a different equation? This is the part that I'm going to show you next, okay? Because there actually is a different way to do this. You get a little bit different equation, but it's still 100% correct, okay? So this is if you set up your parabola like this at these points with the origin involved. Okay? What happens if you didn't set it up that way? In other words, if I go back to my e-tool, what if I set the fence at the origin? So instead of starting at 0 and going to 8, what if I started at -4 and went to +4 and had my vertex along the y-axis? I can do that, right? Totally do that. Okay, let me just show you this to show that there is in fact two distinct possibilities for this. So the y-axis is going to be our fence. It goes up 3, right? So 0, 3 is our vertex. He starts 4 feet out this way, so at -4, 0. And he ends at 4 out this way, so 4, 0, right? So this is the path that our little rabbit is going to take. Okay, totally correct, right? Totally correct. Okay, so in this one, A times x minus 0, usually write the 0, plus k. Not plus k. Oh my lord, you know what k is? It's 3. Okay, so now I can get rid of the 0. I mean, technically, I could write it like this, right? Because we just don't usually write zeros because it's weird. Okay? All right. Now, choose a point. Doesn't matter which one. You have this point on your parabola. You have this point on your parabola. It does not matter which one. All right? Let's use, I don't know, let's use -4, 0. Why not? Okay? -4, 0 is the point that we're going to plug in so we can figure out what A is. 0 equals A times -4 squared plus 3. Okay? So 0 equals 16A plus 3. Maybe you're seeing what's happening here. Look at our A value. Ends up being exactly the same as the other one, right? Yeah, because even though we shifted that parabola over a little bit to the right, it's still going to have the same stretch factor because we didn't change the shape of the parabola. We just changed the starting and ending point, right? So yeah, you should get the same A value. So then final answer for this vertex, -3/16, samesies, x squared plus 3. Totally correct. All right, how about the domain for this baby? -4 to +4. I almost wrote 0. No. Okay, the range 0 to 3. So the range stayed the same. Here we go. Okay, so that's what they meant by having a different equation and having it still be correct. And I mean, and technically, like, you could technically start and end anywhere you wanted to, really. I mean, these are the most common, but like if you wanted to start at -1 and go to 7, you could do that too, right? If you wanted to start at -8 and go to 0, you can do that too. That part doesn't matter, okay? What matters is that you know how to find the A regardless of where you position your parabola on the coordinate plane. All right, I'm going to help you get set up with problem 66. Most of the work is going to be your responsibility, but I'm just going to help you get started. All right, when Ms. Beebe kicked a soccer ball, it traveled a horizontal distance of 150 feet and reached a height of 100 feet at its highest point. Sketch the path of the soccer ball and find an equation of the parabola that it models. Now, remember, based on yesterday, you can start your parabola at the origin and move in the positive direction, or you can shift it and use that y-axis as your vertex, okay? I'm gonna leave that part up to you. Generally speaking, whenever you kick a ball, whether it's a soccer ball or a football or whatever, it makes the path of a parabola, or what we call a parabolic path. Note, this is an upside down parabola. Keep that in mind because that's going to play a part in your final equation, all right? Either way, regardless of where you start, whether you're starting at the origin or you're starting elsewhere, this distance is 150 feet across. Okay, that is the horizontal distance that it covers. The vertical distance, or the maximum height, is 100 feet. So that's the part that's going to affect your vertex. Okay, now the rest of it, I'm going to leave it up to you. All right, you figure out the equation. You figure out, what the A value is, the H value, the K value, all of that. Okay, let's take a look at 67. Again, I'm just going to give you just a visual so that you know what it looks like, but I'm going to leave the rest of it up to you. So 67 states, at the skateboard park, the hot new attraction is the U-dip, a cement structure embedded into the ground. The cross-sectional view of the U-dip is a parabola that dips 15 feet below the ground. The width at ground level, its widest part, is 40 feet across. Sketch the cross-sectional view of the U-dip and find the equation of the parabola that it models. So this one, like if this was ground level, this dip goes down like this, and then again, there's the ground level, okay? So it says that it dips 15 feet below. Obviously, I did not draw this to scale now that I'm looking at it, but that's okay. So 15 feet below the ground, and then at its widest part, meaning up here, this is 40 feet. So again, depending on how you want to set this up, do you want to start at the origin and go in the positive direction, or do you want to use that y-axis as your vertex, or I guess it would be down here for this one, to write your equation? Now remember, this one is a right, I guess like a right side up parabola, okay? So keep that in mind when you're writing your equation.